Hello, my name is Willie Chan. I am the lead author and developer of Phenotate, a phenotypic annotation project and web-based application for genetic diseases, specifically rare diseases. This project was started at SickKids and is now based in the University of Toronto. Before we begin discussing Phenotate, here is a short video made by my colleague Alex Lozano to give you a preview of what it's about.
Phenotate is a platform to crowdsource phenotype data about diseases. Phenotate allows researchers to enter in a disease they'd like to study, and then invite users to collaborate and add phenotype data for that disease. Developed at SickKids and the Department of Computer Science at U of T, it will allow us to build a curated library of accurate, machine-readable disease annotations that can be used for many applications. As a researcher, you make an account and begin by entering the disease you wish to study. You then invite others to annotate your disease with phenotype data. Our most exciting use is in the classroom. As a professor, you can make assignments and projects for your students that generate valuable data about a disease. In the project, you invite your students to scan the literature and start adding phenotypes for the disease, each of which must be referenced. You can give your students a grade, or the software can assign one based on how thorough the answers were. In doing this, your students are learning about genetics and disease while crowdsourcing new information. Any novel phenotype-genotype relationships they find in the literature will lead to a better understanding of that disease.
Thanks for watching. We hope you enjoy using Phenotate.
When we discuss rare diseases, although each individual disease is rare by definition, the number of patients with rare disease is estimated to be 260 to 440 million individuals worldwide. It's difficult to treat rare disease patients because each disease is so rare, so they can be left undiagnosed for a long time. Fortunately, we can use computational approaches to document each disease and improve patient care. Here are two projects that also originated from SickKids, which do just that. First, Phenotype is an electronic health record system for genetic diseases. As you can see, physicians can enter in symptoms and receive suggestions for diagnosis. Of course, this does not replace actual doctors, but you can see how we can narrow down to rare diseases that most people have not heard of. Other tools, like Exomizer and Genomizer, can then be used to identify genetic variants linked to the disease. Next, this is Phenome Central. It's a tool that's part of the Matchmaker Exchange, a system for connecting patients with rare diseases and their doctors around the world using the genotypic and phenotypic profiles. It works similar to Phenotypes, but rather than showing you disease suggestions, it outputs a list of similar cases and allows doctors to reach out to their counterparts in another part of the world. As you can see, care for rare disease patients can be improved with software, but these tools don't work unless they are accurate and computational annotations of genetic diseases. For many diseases, these annotations are incomplete. Most of these information exist in free-form text in literature, such as those documenting case studies and experiments. Now, you can write a program that parses natural language and extracts the annotations from literature, and given today's advanced language models, this would be an excellent way to approach this task. However, this project is focused on crowdsourcing annotations from students and researchers. So, we built a web application called Phenotate for students and researchers to contribute to computational medical genetics and help understand rare diseases by annotating them with phenotypes. For the remainder of this talk, I will demonstrate how to use Phenotate to enter annotations of diseases, and I will also talk about our paper, where we demonstrate that we can compile student annotations of diseases into composite annotations with reasonable accuracy. Alright, so let's head over to phenotate.org and create an account. Click Sign Up, then fill in the details. You should have received a join code for your class. Paste in the join code here. If you forgot to enter the join code, you can do it later by clicking Join Class. Now, go to Exercises, then click on the exercise. Keep in mind that there is no time limit other than the due date, and there is no save button, because Phenotate autosaves, so you can pick up where you left off. First, choose a disease to annotate. You will have to annotate each disease before submitting the assignment. We generally only grade one of the diseases, but we don't announce which disease, and it's not always the more common one. Next, you have to refer to the literature. You can only cite papers that constitute primary sources. Secondary sources, book chapters, and websites are not accepted. If you see a review that discusses the disease you are annotating, be sure to check its reference section. Alright, let's enter phenotypic data. Click on the left part of the orange bar at the bottom of the screen. This box accepts the name of the phenotype and all kinds of variations thereof, including synonyms and typos. Select the phenotype you want to add. The blue I button opens the Phenotype browser, where you can select a phenotype that is more or less specific than the one you entered. If you already added the phenotype, you can expand the phenotype box, then click the I button. With the phenotype box expanded, you can select the age of onset and frequency, if available. You can provide a range of ages and frequencies as well. Each phenotype must be associated with one or more references. To cite a reference, enter the title or the PubMed ID in the right-hand part of the bottom bar. If you cannot find the paper, we apologize for the less than ideal search tool. Please enter the title into Google or PubMed, then select the PubMed result. Copy and paste the PubMed ID into the box. To associate the reference to a phenotype, just drag and drop. If you are on Safari, or if you cannot drag and drop with your input device, click the plus button on the expanded phenotype box. Then enter the reference number. Click on the reference number in the expanded phenotype box to remove the association. You can associate one paper with multiple phenotypes. Once you've entered all the phenotypes and references you would like to add, just click Submit. And that's it. Note that this is just an example, and you should probably have more than one phenotype. If you need help using Phenotate, please visit phenotate.org/documentation or click Help on the left sidebar. You can also contact us at support@phenotate.org or use the message box at the bottom right corner. Keep in mind that even after annotating the assigned diseases, you can continue to annotate more diseases using our gamification system in the dashboard, where you can earn in-app points and rank in our leaderboard. Great, let's talk about the paper now. Here's what we do with the data you enter. Suppose we have two diseases, each with a set of annotations by the same students. In other words, each student annotated both diseases. One of the diseases, which we'll call this known disease, is scored against a standard annotation. The other disease, which we'll call the target disease, is unscored. Our goal is to generate a composite annotation of the target disease based on how well students did on the known disease. If one student does better than another student on the known disease, then we would want to weigh the former student's annotation more when compiling the composite annotation. First, we score each student's annotation of the known disease using the Jaccard formula. For every observed phenotype in a student's annotation, we expand the annotation by adding phenotypes that are more general than it. For example, if the student selected absent seizures as part of the annotation, we would add dialeptic seizures, generalized seizures, and abnormality of nervous system physiology if they aren't already in the annotation. We do the same for the standard annotation. This allows both annotations to be compared even if one annotation uses more specific phenotypes than the other. Currently, our method does not utilize phenotypes that are marked as not observed. We then take the number of phenotypes in the modified student annotation that are also in the modified standard annotation and divide by the total number of phenotypes in both annotations. This gives us the score of the annotation. Please note, although this is the standard method of comparing annotations in our lab, this is not how we grade your annotation for course credit, and you will never see this score. Scores for course credit are assigned by a human grader who takes into account the phenotypes you select and the references you cite. Next, we take all the student annotations of the target disease, modified by adding more general phenotypes, and format them as a P by N matrix, where P is the number of unique phenotypes and N is the number of students. Each cell of the matrix is either positive 1, which indicates that the student marked the phenotype as observed, or negative 1, which indicates otherwise. We then multiply this matrix by the vector of scores, thus scaling each annotation and phenotype by the score of the known disease and summing up the values of each phenotype. Lastly, we apply a sigmoid function on the vector of the sum phenotype values to determine whether to include the phenotype in our composite annotation. Sigmoid outputs are generally either 0 or 1, but in case they fall somewhere in between, we set a threshold of 0.5 for inclusion in our composite annotation. However, before applying the sigmoid function, we multiply the phenotype values by a number we'll call theta 0, and add to the product, a number we'll call theta 1. These two thetas are our parameters that the model needs to learn. To learn these parameters, we use a matrix of the student annotations of the known disease instead of the target disease, and try to get the composite annotation to resemble the standard annotation as much as possible. As in most other machine learning projects, we use the similarity between what we predict and what we assume to be true, then adjust our theta parameters so the annotations will be more similar next time. This cycle is repeated for 100,000 times. We use the same theta parameters for the target disease in order to generate the composite annotation. We assume that the trained parameters for the known disease can be generalized to the target disease. That's about it for our machine learning method. We admit it's not the best method, since many machine learning projects nowadays use much more complicated models and neural networks, but it's sufficient for our purposes. Because we were looking to validate our methods, we assigned diseases that were all basically known diseases that we have standard annotations for. The standard annotations originated from partner organizations and also Brittany Johnstone, co-author and our lab's former genetic counselor. We also collected annotations from clinical geneticists in a workshop held in 2014, before I joined the lab. In our paper, we used data from 5 classes, with annotations describing 22 diseases. Our largest class has 87 participating students annotating 3 diseases, which the clinical geneticists also annotated: Marfan syndrome, Friedreich ataxia 1, and presynaptic congenital myasthenic syndrome 6, or CMS6 for short. We found that our composite annotations were closer to the standard annotations than those put together by clinical geneticists. However, the clinical geneticists were working under memory and limited time constraints, since they created the annotations during a workshop. Although we point out that clinical geneticists have extensive medical training and clinical experience. When we look at the individual phenotypes entered, we see that our composite annotations included some phenotypes not listed in the clinical geneticist annotations. For example, Ectopia lentis is an important phenotype for Marfan syndrome. It is listed in many students' annotations and also our composite annotation, but not in clinical geneticists. The same goes for dysarthria, an important phenotype for Friedreich ataxia. In our composite annotation, not only do we have dysarthria, but we also have gait ataxia, while clinical geneticist annotations list only the much less specific phenotype ataxia. Sometimes, one clinical geneticist will list phenotype A but forget to list B, and another clinical geneticist will list B but not A. This is the case for apnea and bulbar palsy in CMS6, but because we have annotations from many students, each with a weight or trustworthiness measure, we can intelligently combine these annotations and therefore list both phenotypes accurately. Experts can make mistakes, and they may not be entirely familiar with every genetic disease. With our crowdsourcing methods, we get many non-experts to contribute, then pool their inputs together. But you may be wondering, how many non-experts or students do you need? We have 73 sets of annotations from this class, so we sampled percentages of these annotations, from 10% to 100%. We ran our experiment 10 times per sample size, then averaged the results. As you can see from this graph, the more annotations we had, the better our composite annotation. However, even if we took just 10% or 7 of our annotations, the F1 scores dropped by only 10 to 15%. So it's better to have more annotations, but we can still get by with a few. Notice that our model scales well to the number of annotations, so the F1 score we get reflects how many annotations we use. While our primary goal is to generate composite annotation, Phenotate is a learning tool after all, so we investigated how well students did on the annotations. We don't expect students to be familiar with the specific rare diseases before completing the annotations, but we want them to come up with comprehensive annotations, which demonstrates they have gained knowledge while annotating the diseases. We use sensitivity and specificity scores. Sensitivity is the number of correct phenotypes annotated by a student divided by the number of phenotypes in our standards. Within the scope of all phenotypes selected by the class, specificity is the number of correctly omitted phenotypes, including phenotypes correctly marked as negative, divided by the number of phenotypes not selected by a student, including negative phenotypes. As you can see in these histograms, most students score well on both metrics. In later years, we collected annotations from 4 additional classes at the University of Toronto and University of Waterloo for 19 additional diseases. There was some variation between how each class used Phenotate, but students had a week to several weeks to complete the annotations. One class used Phenotate as an in-class activity, in which case students had only 15 minutes to complete the annotations. All the metrics can be found in our paper. Note that some diseases did not have standards at the time of data analysis, so metrics would not be available for those diseases. We also generated receiver operating characteristic, or ROC curves, for each target disease. Recall that our model outputs a number between 0 and 1 for each phenotype, and we typically set 0.5 as the threshold for inclusion in our composite annotation. We can adjust this threshold to include more or less phenotypes. In other words, make more phenotypes positive and less phenotypes negative, and vice versa. An ROC curve plots the true positive rate versus the false positive rate as we adjust this threshold. The greater the area under the ROC curve, the better our model performs. As you can see from our ROC curves, we obtain high areas for most diseases. A closer look at our composite annotations showed that our composite annotations capture the most frequent phenotypes in our standards, as well as several phenotypes that are occasionally present in patients. Our composite annotations have high precision scores, which means the phenotypes in our annotations are highly relevant to the diseases. So we've got these composite annotations. Are they useful for clinical applications? To find out, we took the composite annotations for 20 diseases and paired them with annotations for the same diseases from other sources. We asked 2 clinical geneticists at SickKids to identify the diseases. They did not know which annotations were generated by our algorithm and which were obtained from other sources. Each clinician received 1 annotation for each disease, so if one clinician received the composite annotation for Marfan syndrome, the other clinician will receive this other annotation for Marfan syndrome. They were asked to fill out a questionnaire that asks for the disease name and how certain they were on a scale of 1 to 5. They were able to identify 13 composite annotations and 15 other annotations, and their confidence for our annotations are slightly lower by half a point. Although 13 is less than 15, and they weren't as confident at identifying diseases using our composite annotations, we argue that the numbers are close enough and the diseases are generally difficult to identify, as many of them are extremely rare. We also asked clinicians to compare the annotations for 6 diseases. Remember that they don't know which annotations are from us. Overall, they showed equal preference between our composite and other annotations. For the diseases where our annotations are more preferable, clinicians expressed that our annotations are more concise, specific, and accurate. To sum up, we use machine learning methods to process student annotations and generate composite annotations that are high quality and can be used in clinical applications, including patient diagnosis. Collectively, we demonstrate that students can generate annotations that are comparable or even better to those generated by clinical geneticists, even though as experts, geneticists have extensive medical training and clinical experience. Furthermore, Phenotate is an educational tool that can be used in genetics courses and training programs. We think students can benefit from using Phenotate to learn about rare diseases, and we hope that you will enjoy using it. Remember, the annotations you enter will benefit the rare disease community. We appreciate your participation in our project. Thank you. This project has received funding from the European Union's Horizon 2020 Research and Innovation Program under the ERANET Co-Fund Action number 643578. It was supported by the Canadian Institutes of Health Research and Genome Canada under the frame of eRare3, the ERANET for research on rare diseases. Data analysis for this project was performed by co-author Puriya Mashori.